Let omega be the unit circle in the xy plane in three-dimensional space. Find all points P not on the xy plane that satisfy the following condition. There exist points A, B, and C on omega such that angle APB is equal to angle APC is equal to angle BPC is equal to 90 degrees. And in this video, we're going to be proving that P must lie on the ellipsoid x squared plus y squared plus 2z squared is equal to 1. The x, y, and z coordinates of P satisfy this. And so how do we get such a funky answer? So let's go ahead and prove this. So first we note that P lies on the spheres with diameters AB, BC, and CA because we have right angles here. So we have our sphere here. Sorry if it's kind of weird. And we also have spheres for the other ones. And then there we go. And this motivates us because the center of the spheres lie on the sides. This motivates us to look at it from the top. And if we look at it from the top, then we see that when we have A, B, and C, that CP appears to be perpendicular to AB. So conjecture is that CP is perpendicular to AB. And similarly, BP is perpendicular to AC, and AP is perpendicular to BC. And in particular, this means that P is the orthocenter of the triangle. So how do we get started on proving this? To prove this, I've drawn in the three spheres here. So as we see, P lies on these three spheres with diameters BC, AB, and AC. And we have that P is the intersection lies on all of them. So if we want to find the intersection of all of these three spheres, it might help to consider two of them first. So here are two of the spheres here, specifically the spheres with diameters BC and AB. And we want to find out what their intersection is. And as we see here, they seem to intersect on BC itself. And actually, this is pretty obvious because this point here, let's call it D, suppose, is the foot of the altitude from B to AC because angle BDA is 90 degrees. So that means that angle BDA is equal to angle CDA is equal to 90 degrees. Moreover, the spheres are symmetric about the xy plane, which means that the intersection is just a circle with diameter BD, but it's perpendicular to the xy plane. Now we draw the circle with diameter BD perpendicular to the xy plane. And we know that P lies somewhere on this circle here. In particular, because P lies on this circle with diameter BD, its projection onto the xy plane must lie on the line BD. So we only know that P lies on line BD. Well, but because this argument is symmetric, we know that P lies on the other three altitudes, and therefore the projection of P onto the triangle is the orthocenter, as we claimed. Now that we know that the projection of P onto the xy plane is the orthocenter, we can truly start working on the problem. What we want to show is that OH squared, because that is equal to x squared plus y squared, plus 2ph squared, which is equal to z squared because pH is perpendicular to the plane. We want to show that the sum of these two is equal to 1. And now to find out what pH squared is, we can end up using right triangle APB. And note that HP squared plus HB squared is equal to PB squared. And then HP squared plus HA squared is equal to PA squared. And then adding the two, we end up getting 2HP squared plus HB squared plus HA squared is equal to AB squared because AB squared is equal to PB squared plus PA squared because it's a right angle. And solving for 2ph squared, we end up getting 2ph squared is equal to AB squared minus HB squared minus HA squared. And plugging back into this thing here, we reduced it to showing OH squared minus HB squared minus HA squared plus AB squared is equal to 1. So how do we go about proving this? We want to show this expression holds for a triangle ABC inscribed in the unit circle. And we have an orthocenter and a circumcenter thrown in here. So what do? Well, you know it, we use complex numbers. If you haven't already, watch my video on complex numbers, which I'm going to link in the description. Anyway, we have that the complex number representing O is just the number 0. And then if the complex number representing A is A, then B is B, then C is C, then we know that the orthocenter is A plus B plus C from that video. And therefore, we end up having OH squared is equal to the magnitude of A plus B plus C squared. And from what we know about complex magnitudes, this is equal to A plus B plus C times its conjugate. And the conjugate of A is 1 over A, so it's 1 over A plus 1 over B plus 1 over C, which is 3 plus A over B plus B over A plus C over B plus B over C plus C over A plus A over C. And now we have that HB squared, similarly, is H minus B squared. So that's A plus B plus C minus B. So that is the magnitude of A plus C squared, which is A plus C times 1 over A plus 1 over C, which is 2 plus C over A plus A over C. Similarly, HA squared is equal to 2 plus B over C plus C over B. And finally, we have that AB squared is equal to the magnitude of A minus B squared, which is A minus B times 1 over A minus 1 over B, which is 2 minus B over A minus A over B. Therefore, when plugging into this expression here, we end up getting 3 plus A over B plus B over A plus C over B plus B over C plus C over A plus A over C minus, we first have 2 plus C over A plus A over C, and then this causes these terms to cancel out. Then we subtract 2 plus B over C plus C over B, and then these terms cancel out. And then we add 2 minus A over B plus B over A. And then these terms also cancel out. And all we are left with is 3 minus 2 plus 2, which is 1, as we claimed. Therefore, working backwards, we see that the point P must lie on the ellipsoid x squared plus y squared plus 2z squared is equal to 1. And if we want to show that every point P on this ellipsoid has a choice for A, B, and C, then we just need to construct a triangle with a given orthocenter and circumcenter, and we can just use what we showed. And it's easy enough to construct a triangle with a given circumcenter and orthocenter, and I'll go ahead and let you guys figure that out on your own. So thank you so much for watching this video. Please subscribe if you'd like to see more.